In this lecture, we're going to introduce sequences and summation notation. Let's start with an informal definition of a sequence. A sequence is just a list of numbers. It's an ordered list of numbers that are not necessarily distinct from one another. You can have the same number over and over again in a sequence. More formally, a sequence is thought of as a function whose domain is the set of natural numbers. At least an infinite sequence can be defined that way. But we don't need to be that nerdy. A sequence is just a list of numbers. We often denote the nth term of a sequence by the notation a sub n. So the first term would be a sub 1, the second term would be a sub 2, and so on. Not only is this a convenient way to pick out specific terms of the list, but we can also use a sub n to represent the formula. If there's some sort of formula that generates the terms of the sequence, we can call that formula a sub n. One more bit of notation. To specify that a formula is generating terms of a sequence, we trap the formula in these little set braces. So if a sub n is a formula for the nth term of a sequence, then we denote the sequence by trapping that formula inside the curly braces. So for example, here we're asked to find the first three terms and the 100th term of this sequence generated by the formula 2n minus 1. The curly braces here indicate that this is the formula that generates the terms of the sequence. Another way to say this is that the nth term a sub n is defined by 2n minus 1. We're told to find the first three terms and the 100th term. The first term of the sequence would be a sub 1. And now we see how the formula works. To find a sub 1, we plug 1 in for n. This is just like function notation, except instead of using parentheses around the input, we're using a subscript. But otherwise, it's the same thing. So now we do the calculation. 2 minus 1 is 1, and so the first term of the sequence is 1. The second term of the sequence would be a sub 2. That would be 2 times 2 minus 1, which is 4 minus 1, which is 3. So the second term is 3. The third term is 2 times 3 minus 1, 6 minus 1, which is 5. At this point, you might have a pretty good hunch at what this sequence is. If you're guessing that this sequence is the list of positive odd integers, you're absolutely correct. This will generate all of the positive odd integers in order from smallest to largest. We're also asked to find the 100th term of the sequence, and now that we've guessed what the sequence is, I guess we could keep listing the entries until we got to the 100th one, but that's not the most efficient way to do it. We can jump straight to the 100th term by just plugging 100 in for n. The 100th odd number in this list would be 2 times 100 minus 1, which is 200 minus 1, or 199. So after quite a few more terms, this sequence will eventually reach 199 in the 100th spot, and then it will continue on. So the curly braces are a way of indicating a sequence, and the formula inside of the curly braces tells us how we generate the terms of that sequence. Let me give you one to try. I want you to find the first three terms and the 50th term of the sequence generated by the formula n squared over 3n plus 1. Pause the video and see if you can come up with the first three terms and the 50th term. This notation is telling us that the nth term of our list is generated by the formula n squared over 3n plus 1. So if I want to find the first term, I plug 1 in for n. That's 1 squared over 3 times 1 plus 1, which is 1/4. So the first term of our sequence is 1/4. The second term of our sequence is 2 squared over 3 times 2 plus 1, which is 4/7. The third term would be 3 squared over 3 times 3 plus 1, which is 9/10. And this list continues, and eventually we'd reach the 50th term, which we get by 50 squared over 3 times 50 plus 1, which is 2,500 divided by 151, and then the sequence would continue from there. Let's look at one more example, a special case. Let's find the first three terms and the millionth term of this sequence. Now here we just see a number inside of the brackets. So this is called a constant sequence because it's not going to change. The nth term is always 3. There's no variable on the right side to change the output of this expression. So the first term would be 3, the second term would be 3, the third term would be 3. Every term is 3, in particular the millionth term is 3. This is a constant sequence. It doesn't change. It's always 3. 3's forever. Now there are lots of different things that you can do with sequences in math, but we're going to see them as part of summation notation. Summation notation is pretty much what it sounds like. It's a way to denote a sum. It's a way to say that you're going to add up a bunch of things. More to the point, the sum of the first m terms of the sequence a sub k is denoted in the following way. We use the Greek letter sigma. This is the uppercase version of the Greek letter sigma here. This funky looking E, that's an uppercase sigma. That's the notation that says we're going to add up a bunch of things. Next to that, you put the formula for the sequence. You don't trap the sequence in the curly braces. You just put that formula off to the side. At the bottom of the sigma notation, we write which term we're going to start the sum with. So if we're adding up the first m terms, then we're going to start with the first term, so it says k equals 1. At the top, we write the position of the last term of the sequence. So we're going all the way up to the mth term so that we can add up the first m terms. So in other words, this notation is saying start with the first term of the sequence and then continue adding the terms until you reach the mth term of the sequence. This tells you where to stop. The bottom number tells you where to start, and the top number tells you where to stop. If you want to start at some other term other than the first term, like suppose you wanted to start at the nth term, then you would just write k equals n at the bottom. So if you wanted to start adding with the third term, you'd write k equals 3 on the bottom. If you wanted to start with the 8th term, you'd write k equals 8 at the bottom. The bottom number tells you which term to start with, and the top number tells you which term to end with. When we talk about it abstractly, it seems complicated, but this actually isn't too hard. We're going to find this sum. The sigma notation here tells us that we're finding a sum. We're finding a sum of terms of the sequence generated by the formula k cubed. So we're going to be adding up a bunch of cubed numbers. Which cubed numbers are we going to add together? Well, we're starting with k equals 1 and ending with k equals 5, so that's the first 5 terms of the sequence. We'll take this example slow and generate the terms off to the side. The formula for our sequence is a sub k equals k cubed. We're going to start with the first term of that sequence, a sub 1, which would be 1 cubed, which is 1. So we're starting with 1. Then we go to the second term, a sub 2, 2 cubed, which is 8. Then we generate the third term, 3 cubed, which is 27. The fourth term, 4 cubed, which is 64. And then the fifth term, 5 cubed, which is 125. And that's the last term. And how do I know to stop there? Because the top number tells me that I go all the way to the fifth term. Start with the first term and keep generating terms until you get to the fifth term. The sigma notation tells us to add all of these up. We're going to find this sum. 1 plus 8 is 9, 9 plus 27 is 36, 36 plus 64 is 100, 100 plus 125 is 225. We've now found the sum of the first 5 terms of the sequence generated by the formula a sub k equals k cubed. Let's try another one. This says find the sum from k equals 1 to 4 of 1 over k squared plus k. Again, we're going to take this slow. This is the formula for some sequence a sub k. Our notation here is telling us to add up the first 4 terms. How do I know I'm starting with the first term? Because the bottom says k equals 1. How do I know I'm going all the way up to the fourth term? Because the top number is 4. So I need to find the first term, the second term, the third term, and the fourth term of this sequence. The first term would be 1 over 1 squared plus 1, which is 1/2. The second term would be 1 over 2 squared plus 2, which is 1/6. The third term would be 1 over 3 squared plus 3, which is 1/12. And the fourth term would be 1 over 4 squared plus 4, which is 1/20. This notation is telling us to add those 4 terms together. 1/2 plus 1/6 plus 1/12 plus 1/20. If I want to add these by hand, I need to get a common denominator. The least common denominator is 60. 1/2 is 30 over 60, 1/6 is 10 over 60, 1/12 is 5 over 60, and 1/20 is 3 over 60. Adding those numerators together, we get 48 over 60, and 40 over 60 reduces to 4/5. So the sum of the first 4 terms of this sequence is 4/5. So when the bottom number is a 1, you're just finding the sum of the first few terms of the sequence. How many terms? Whatever number is on top. The sequence is generated by the formula written to the right of the uppercase sigma notation. The sigma is what tells us to add. Let's do an example where the bottom number isn't 1. Here's an example that looks kind of strange. This says find the sum from k equals 0 to 3 of 2 to the k. Now I know there isn't really a 0th term in a list. You can't have a 0th term. But we extend the idea to still just mean plug in 0 for k. So a sub k is this formula 2 to the k. So a sub 0 would be 2 to the 0, which is 1. A sub 1 would be 2 to the first, which is 2. A sub 2 would be 2 squared, which is 4. And I stop at a sub 3 because the top number is 3. A sub 3 would be 2 cubed, which is 8. So this is telling us to add those 4 terms together, and that's 15. Here's another one for you to try. This is the sum from k equals 5 to 7 of 2k squared. I want you to generate the terms that we're adding together and then find their sum. Our formula is a sub k equals 2k squared. We're going to start with k equals 5. That's 2 times 5 squared, which is 50. Then we do 6, which is 2 times 6 squared, 72. And we stop with 7 because that's the number on the top. So 2 times 7 squared, which is 98. So we're finding the sum of these 3 terms, 50 plus 72 plus 98, which is 220. This says find the sum from k equals 1 to 50 of 4. Here we're finding the sum of the first 50 terms of the constant sequence that always generates 4s. Now when you say that at first, it sounds like it's going to take a long time because we're adding up 50 terms. But let's take advantage of the fact that they're all 4s. The first term is 4 and the second term is 4. And we just get 50 copies of 4 added together. There are 50 terms here. We know a shortcut for this. Repeated addition can be replaced by multiplication. This is just 4 times 50, which is 200. If we're repeatedly adding the same number together, we just take that number and multiply it by the number of copies. That gives us the sum. With that in mind, I want you to do this example. The sum from k equals 8 to 13 of 10. A common mistake is to put 50 here. A lot of people will take the 13 minus 8 to try to count the terms, but let's be careful this time. A sub k is the sequence that constantly generates tens. I need to use the 8th term, and the 9th term, and the 10th term, the 11th term, the 12th term, and the 13th term. How many tens is that? It's not 5, it's 6. This is 10 times 6, not 10 times 5. Again, a common mistake is to subtract these to try to count, but that doesn't work. Look back at the last example. This was the first 50 terms. But if I subtract these two numbers, I don't get 50, I get 49. I come up 1 short. That's in fact happened in every example. In this example that I asked you to do, we didn't get 2 terms, we got 3 terms. 7 minus 5 is 2, that's 1 short of the number of terms. That rule always works. So 13 minus 8 is 5, that's 1 short of the number of terms we're actually going to generate. We're going to generate 6 terms. Okay, one last bonus idea because I can't help myself. A lot of these sums can be written as formulas. You can actually come up with a formula for the sum of the first n terms. And this is one topic in math that I really find interesting. So I'm going to bore you a little bit with an example. Our very first example of a sequence was this sequence 2n minus 1, which generated the odd numbers. What we're going to do is try to guess the sum of the first 100 terms of that sequence. In other words, that's the sum of the first 100 odd numbers. Now, how are we going to make a guess at that? Well, we're going to find some partial sums and look for a pattern. A partial sum means just add up a few of the terms. So what I'd like you to do is find the sum from k equals 1 to 3 of 2k minus 1, the sum from k equals 1 to 4 of 2k minus 1, and the sum from k equals 1 to 5 of 2k minus 1, and see if you notice a pattern among those answers. If you see a pattern, I want you to use that to guess the sum from k equals 1 to 100 of 2k minus 1. Okay, let's find these sums. Because the bottom number is k equals 1, we're going to start with the first term of this sequence. And we've already said this sequence generates the positive odd integer, so the first term of that sequence is 1. The second term is 3, and I stop with the third term here because the top number is 3. 1 plus 3 plus 5 is 9. The next one's just asking for the sum of the first 4 terms of the sequence. So I start with those first 3, and then I tack on the next odd integer, which is 7. That would be 16. The next one says do the first 5 odd integers. Well, that's the 16 we got last time plus 9, which is 25. Do you recognize the pattern? The answer is just the square of the number on top every time. If that pattern holds, then our guess would be that this sum is 100 squared, which is 10,000. And it turns out that that's true. We can actually write this as a general formula. The sum from k equals 1 to n of 2k minus 1 is always just n squared. Now it's important you start with k equals 1, but as long as you start with k equals 1, this sum will just come out to the top number squared every single time. So dorks like me think it's neat that every time you add up the first n odd integers, you wind up getting n squared. That's kind of a surprising result at first. And there are lots of other interesting sums. Like some of the examples I did in this video have some pretty interesting patterns that they follow. Here we've got the formulas for some of the sums that we did in this video. If you know these, they're like shortcuts to the answers. You don't have to actually add up all of the individual terms. I've always thought that these formulas for sums were interesting, so when I'm sitting around doing math for fun, this is something that I might do. And I know the phrase doing math for fun might sound ridiculous to you, but some people sit around and doodle, draw pictures. Well, I can't draw, so my doodling is to do math problems, and this is something I would do. I just think this stuff's neat. Now, you don't need to know how to find these formulas or even how to use them. You just need to be able to find the sum of the first few terms of a sequence, like we did here, or in our first example. If you have questions about this summation notation, or if you've got a little bit of nerd in you and you want to talk more about these dorky formulas at the end of the video, just reach out to me by email or see me in an office hour.